Hi, everyone. In this lesson, we are going to do some problem solving with combinations. Our last lesson, we learned about combinations, so groups of objects or elements where order does not matter. And today we're just going to apply that to a variety of problems, maybe develop some new rules along the way. So here we go. It's a bit of motivation. We're going to imagine how many different sums of money you can make with various denominations of coin. Might do the first one or two with you, and then you can see if you can figure out the final few. So if you just have a single penny, it is, it's fairly straightforward. You can either have nothing, right? Or you can have the penny. Those are two different sums that you can make, right? You could have, if you don't have, you could have $0, or you could have just the penny, and that's $1. So pretty straightforward, two sums. As you add more coins, it's a bit more complicated. So with a penny and a nickel, we could have, again, nothing and make $0. Or we could have the penny by itself and make a cent. Or we could have the nickel by itself and have 5 cents. Or you could have the penny and the nickel at the same time, and that makes 4 sums of money when we have 2 coins. That should be part B. Why don't you guys try the next part C? If you have a penny, a nickel, and a dime, how many sums can you make? I believe after this one, if you try to list them all out, you should be starting to see a pattern that maybe you could predict the number of objects you could, or the number of sums you can get with part D when you have 4 coins. So if you want to pause and try these on your own, that's fine. But if you want to follow along with me, you can too. So when you have 3 coins, you can have nothing. And then you could take a single coin. So you could have like a penny, a nickel, or a dime. So it's like 1 cent, 5 cents, or 10 cents. Or you could grab 2 of them, right? So you could have the penny and nickel, or the penny and the dime, or the nickel and the dime. And that gives you, 6 cents, 11 cents, and 15 cents. Or you could take all 3, penny, nickel, and dime. And that's actually 8 sums. So we go back. With 1 coin, we made 2 sums. With 2 coins, we made 4 sums. With 3 coins, we made 8 sums. I bet you probably see a pattern there, part D. But let me list all the ways you can make a sum of money with these guys. So again, you could have none of them and make $0, or you could take one of these coins at a time: penny, nickel, dime, and quarter, or 2 of them. So penny, quarter, penny, dime, penny, nickel. Can have the nickel and the dime, the nickel and the quarter, and then the dime and the quarter are the 2 biggest guys. And those all make different sums. So that's 26 cents, 11 cents, 6 cents, 15, 30, and 35. Then you could have 3 coins too, right? Like you could take penny, nickel, and dime and leave out the quarter. Or you can leave out the dime, penny, nickel, quarter, or leave out the nickel, penny, dime, quarter, or leave out the penny, nickel, dime, quarter. And these are all different sums. Finally, you could have all of them: penny, dime, nickel, quarter. And this gives you the biggest sum. That's 41 cents. But if you look at all the options here and count those up, 1 plus 4 plus 6 plus 4 plus 1, you get 16 sums altogether. So there's a definite pattern here: 2, 4, 6, 8, 16. So I'm going to do, maybe you've predicted the number of ways you can get penny, nickel, dime, quarter, and a loonie, so 5 coins. I'm going to show you guys 2 methods here. So the first one is kind of like the long way of doing things. So if I'm going to make a sum of money, so I can take no coins, find the number of ways to take no coins, and then I can find out the number of different sums I can make with 1 coin, and then the number of sums I can make with 2 coins, and you can see where I'm going here. With 3 coins, the number of sums I can make with 4 coins, and in this example, we have 5 coins. Thinking back to yesterday, the number of sums I can make with no coins, well, that's just like I have 5 different coins and I'm choosing 0 of them. And then with 1 coin, there's 5 of them, and we're asking, well, how many ways can I choose 1 of them? So that will give me my 5 different sums I can make with just 1 coin. 5 choose 2 is the number of ways to choose 2 coins, and so on and so forth. 5 choose 3, 5 choose 4, and then finally 5 choose 5. If you add up these values, so take a moment and evaluate these guys and add them up, what you'll notice is we do get 32. The pattern continues. 5 coins, 32. Now you may recognize by now these are all powers of 2. It's interesting that all these combinations would add up to a power of 2. It's not surprising when you actually look at the problem in the following way. So I'm going to set up an FCP calculation actually here. Penny, nickel, dime, quarter, loonie. So we're going to think of it this way. With each coin, you can either take it, when you're creating a sum of money, you can either take it and include it in your sum of money, or you can leave it and you cannot include it. This gives you 2 options for every coin. Either take it or leave it. Include it or don't. In every coin, there's 2 options. Include it in the sum or leave it out of the sum. And you can try for yourself. 2 times 2 times 2 times 2 times 2. That is just 2 to the power of 5. And you get 32 different sums, the same answer you got using combinations. That's a real interesting fact. And actually, it works all the time. When you're making a subset from a larger group of objects, it'll always be a power of 2. That's our key idea here. A set of n different elements has 2 to the power of n subsets, including the set with nothing in it. The set with nothing in it is referred to as the null set. So that would be like the case where we didn't pick any coins and we made a sum of 0 cents. We counted that as a sum, even though that didn't include any coins. So this idea of subsets is just making smaller sets, and it includes taking none of them, the null set, and taking all of them. You can see, like in the last question, the null set would be like taking no coins. Just gotta find there it is. The null set was like taking no coins. And you can verify for yourself, 5 choose 0 is equal to 1. And then the last case we choose all 5 coins, that was the full set. And we count that technically does count as a subset. So hopefully you're convinced that the number of ways to choose make a subset, so like 0 or 1 or 2 or 3, all the way up to how many there are in your set, is a power of 2. Kind of showed it there with the coin example. Let's just try a problem here. I'm gonna do this along with you here. So let's say you manage 6 employees and you need to assign staff to a health and safety committee. In this example, it actually doesn't make sense to have a committee of 0 people. By the very nature of a committee, we need to have at least 1 person. So we're going to allow for a committee of 1, but we're not going to allow a committee of 0. So there's 2 ways to do this problem, just like that we did the last question. So using method 1, this is kind of the long way. You have 6 C1 ways to make a committee of 1, and then 6 C2 ways to have a committee of 2. And like so on and so forth. 6 choose 3, 6 choose 4, 6 choose 5, and then finally you can make the committee where everybody's on it, 6 choose 6, and you can evaluate each of those individually and then add them up. If you'd like to do that independently, you can check that you do get 63. There is an easier way though. if we think about our rule, our power of 2 rule for the number of subsets, so we have 6 employees. So the number of subsets is 2 to the power of 6, 64. However, we need to have 1 or more staff. So we're not counting the null set here. So we can just kind of finish off the problem this way. The number of committees that we can make would be 2 to the power of 6 minus 1. So it's this 64 take away 1, 63 committees. So the same answer we get from the previous method. And again, we're taking away 1 because somebody has to be chosen to be on the committee. So this brings us to another key idea. It's actually kind of like related to the previous one, but the number of combinations containing at least 1 item chosen for a group of n distinct items. It's not 2 to the power of n. It would be 2 to the power of n minus 1. So it's very similar to the number of subsets, but if we're looking at the number of subsets where you have to have at least 1, you subtract 1. And it makes sense because you need at least 1 item. Or in other words, you don't count the null set. All right, we're going to just put this into practice and then try a variety of other problems involving combinations and maybe a mixture of problems. So you try this one, see if you can apply this new principle. So a florist has 12 different flowers available. So maybe roses, tulips, 12 different varieties. How many different bouquets can she make? If she needs at least 1 type of flower. My wife would probably not enjoy a bouquet with no flowers, right? So we're not going to count the null set here. You can pause and try this if you'd like, and unpause when you're ready, or do it along with me here. So in this question, we have 12 distinct types of flowers. The number of bouquets, because we're not counting the null set, we would do 2 to the power of 12. You can either take or leave each individual flower. But again, you do take off 1 because you don't count the null set. You don't want to give somebody a bouquet of flowers with nothing in it. So 4,096 bouquets. So a simple calculation. Just got to get used to framing the problem, given what you have. Let's move on and try some different types of problems. So we've now looked at problems where you're taking a subset. So we did n objects, 1 or 2, or at least 1. In this question, we're going to be counting cases, and we're going to use combinations. So in the game of hearts, so hearts is a game where the entire deck of cards is dealt, and so that means if there's 4 players, every player will have 13 cards. Bridge is another game like this, or a variety of card games where you deal at everything. And in the case with 4 people, you would get 13 cards. We're going to find a way that somebody's 13 card hand could contain at least 11 hearts. So we know, first of all, we know in this question, it's a hand of cards. We know that, in my diagram here, everything has been sorted nicely, those 13 cards. But, if everything was mixed up, it'd still be the same hand. So order doesn't matter. We will use combinations. So we have to ask, well, what does at least 11 hearts mean? Well, it means 11, 12, or 13, all 13. That's what at least 11 means. So we have to break this into cases. So case 1, how many ways could we get dealt 11 hearts? So I would think of it this way. So I'm going to set up a little calculation here. So we got to think of, well, how many ways can I get my 11 hearts? And then how many ways can I get my 2 other cards? So we're going to use combinations. So there are 13 hearts in total, and we're choosing 11 of them for our hand. That's the number of ways to choose which 11 hearts you get. The number of ways to get your two other cards, they can't be hearts because we only want 11, right? So of the other 39 cards that are not hearts, remember there's 52 cards in a deck, right? So of those 39, we're choosing two other ones to be in our hand. And of course, FCP says we'd multiply these things because we're getting 11 hearts and two other cards. And you can try this on your own, but you get 57,798 different hands you could have that have at least 11 hearts. What you guys can do is try the remaining two cases. How many ways can you get 12 hearts? And then how many ways can you get a hand that contains all 13 hearts? So if you want to pause it and try that, that's good. Or again, you can follow along with me. So in this calculation, we need 12 hearts and then one other card. Of our 13 hearts, we need to choose 12 of them for our hand, and order doesn't matter. And for the one other card, well, there's 39 other cards to choose from. So, and we're choosing one of them. So you can say 39C1, but you could also just write 39 there because you're choosing one card and there's 39 options. If you try that, you should get 507 different hands that have 12 hearts exactly. And for 13 hearts, it's a little bit easier. You might not even need to do any work for that, but I mean, if you want to get 13 hearts, you're doing 13, choose 13. And we don't really need a space for this, but if you know you're that type of personality and you need to write this in, we're getting none of the other guys, so we're choosing 0. You just get 1, which makes sense, right? There's only one way to get all 13 hearts. You just get all 13 hearts. And if you total those 3 guys up for a grand total, there's 58,306 ways to get at least 11 hearts. Now, if you play hearts like I do, there are certain advantages to actually getting a high volume of hearts in your hand. It gives you a big advantage over the other players. So, you know, somebody who is mathematically inclined might like to know the probability or the chances of getting a hand like this. And we will examine probability in combinations in a couple of lessons. But determining the number of ways this can happen could possibly give you an advantage in a game. All right, let's continue. We're going to do kind of one more problem together. In the first few parts of this problem, we're going to just get some practice, choosing an appropriate method. You guys now have quite a variety of organized counting tools: fundamental counting principle, permutations, combinations, permutations with repeating elements. So we're going to get some practice choosing the appropriate one. So in this question, I've got a new picture frame. And it's illustrated below. I can fit 5 pictures in a row. And let's say I have 8 pictures of Rosie, my dog, to choose from, and 10 pictures of Bryden, my oldest son, to choose from. How many different frame arrangements could I make? And we're going to look at a few cases. So how many arrangements can I make if I'm only using pictures of Rosie? So what you need to do, guys, is figure out which tool am I using here, which calculation. Is it factorial? Is it permutation, combination? Is it FCP? If you want to pause and give it a try, and then unpause and follow along with the answer, you can, or you can just go along with me here. So the key here is we are arranging these pictures. Order does matter. And if there's only pictures of Rosie, it's actually pretty straightforward. Of the 8 pictures of Rosie, we are choosing 5 for a specific order. We're arranging 5, and that's just 8p5. So you can try this one yourself. 8p5 gives you 6,720 different arrangements I can make. If I just want to put my dog in this picture frame. I could do that 6,720 ways. You could do a similar calculation to find out how many pictures of Bryden, or how many arrangements I could have with only Bryden pictures. I've got 10 pictures of Bryden, and I'm putting 5 in a specific order. So we should have a bit more in this case. 10p5 is 30,240. So again, keyword, arrangements, order matters. We're using permutations here. Let's try part C. So at least one picture of Rosie. So that would mean 1 picture, 2 picture, 3 picture, 4 picture, or 5 pictures. So that'd be 5 calculations. And if you feel like doing 5 calculations, you're welcome to do that. It would work. Could be a little time consuming though. In questions that have frame like at least, at most, when there's seemingly a lot of cases, you might want to consider, could the indirect method help me in this problem? And actually it does, because we've almost done all the work. With the indirect method, we find the total number of options. And for us, we actually have 18 pictures to choose from to put in a specific arrangement of 5. So the total possible arrangements I can make is 18p5, which is just over a million, 1,028,160. And if we think about it, either an arrangement has at least 1 picture of Rosie, or it has no pictures of Rosie. And we already did that calculation. No Rosie means all Bryden, right? We've already found the arrangements that only have Bryden in them. We did that earlier. That was 10p5, and we got 30,240. So for the number of arrangements where we have greater than or equal to 1 picture of Rosie, we've got it now, right? We just have to do 18p5 minus 10p5, those two numbers we got there. And we can get at this problem, pretty efficiently. 997,920 different ways to do that. That's a lot more practical. The other option is fairly complicated, and I might actually come back to it. Well, actually, you know what? Part D in this question will illustrate one of those cases. So when we look at this, when we look at the next part of this question, or the next question I have on your lesson sheet. How many picture arrangements contain 2 pictures of Rosie and 3 pictures of Bryden? So in this question, we're going to choose the pictures to go in our picture frame, and then we're going to arrange them. So it's kind of like a multi-layered problem. We're combining some tools we have. So let's think about this. First, let's actually choose the pictures to go in our frame. So for the pictures of Rosie, we want 2 pictures. So of our 8 pictures of Rosie, we are going to choose 10 of them. 2 of them. Right now, we're only selecting the pictures to go in our frame. For Bryden, I want 3 pictures of him. So of the 10 Bryden pictures, I'm choosing 3 of them. So that gives me the number of ways to choose my 5 pictures. This doesn't give you the number of arrangements though. It just gives you the number of possible groups. Now that we've chosen them, we can arrange them. So we've now chosen our 5 pictures. The number of ways to arrange these 5 specific pictures is 5 factorial. So we chose the pictures and then we arrange them. So 8c2 times 10c3 times 5 factorial. That's 403,200 different ways to have 2 pictures of Rosie. If I could quickly talk about the previous question. So what we just did there is, to get 1 picture of Rosie, that means, we kind of talked earlier, that means either 1, 2, 3, 4, or 5. And what we just did in the last question is we actually looked at the case where you get 2 pictures of Rosie. So the work we just did was just for one of those cases where we have 2 pictures of Rosie. So I don't know about you guys, but I don't want to do 5 calculations like this and add them up when I could be more efficient and just use the indirect method. Both would work. If you did 5 of these calculations, added them up, you would get the same answer. It would be worth full marks, but it's not a great use of your time, especially if you're writing an evaluation or exam. You want to be spending your time doing other things and find efficient ways to do problems. So why don't you try this one if you want to pause the video. So think about what we just did together, combining methods, choosing then arranging. Try this problem here. How many different 5-letter codes can be formed from 2 different vowels and 3 different consonants? So we'll consider y a value for this one, or a vowel for this one. I always considered a y to be a consonant, but the resource where I found this problem, it has y as a vowel, and so I'm broadening my horizons here. Let's let y be a vowel. So if you want to pause, try this problem. You can unpause when you're ready, or you can follow along with me right now. So in our 26-letter alphabet, we have 6 vowels: A, E. Can write those out: A, E, I, O, U. Sometimes Y, but here we're counting Y, and that means we're going to have 26 consonants. So we're making a code. Now, the word code definitely implies that order matters, right? So we will order the characters we choose. But right now, we're going to choose the vowels and choose the consonants that go in our code. So for the vowels, our code here is going to has 2 different values. So for 6 values, we're going to choose 2 of them. And then for our consonants, there's 20 of them. And for our code, we're going to choose 3 of those guys, and we'll multiply using the FCP. That gives us the number of ways to choose which letters and vowels will be in our code. But right now, for example, this just gives you a group of letters. We don't have them arranged yet. We have to multiply by 5 factorial because we have 5 letters, and then we've got it. So 6 choose 2 times 20 choose 3, and I think you've got this, but at this point we're just using the combinations button, the permutations button on our calculator. The formula is good for understanding where these final values come from, but at this point in the game, we're understand its combinations. We don't need to use a formula. So just over 2 million codes are possible in this problem. So in this lesson, we did a variety of new problems where we took subsets where maybe we didn't pick a group or arrange all objects. We picked a group, just some of them. Oh, my battery's low. That's okay. We'll finish off here, guys. Case involving subsets. We did cases where we had to count cases, use the indirect method. We mixed in some permutations and talked about cases where we have to select a group and then arrange them, like the picture question or this question. Next step for you guys is, as usual, I have a handout of practice problems. I've told you guys maybe you might want to do these. This question, R3, reflect 3, asks you to make a organization tool to talk about when to use each counting tool. If you look at the answers, the flow chart, you might want to put into your own notes, but that's optional. I also have an assignment posted on the online platform for you guys, talking about work with questions involving the stuff we've done up to this point. All right, guys, that's it for me. Good luck with your work. Please let me know if you need a hand with anything, and we'll see you guys online.